Hello, my name is Lloyd Diamond, and I am the CEO of Pixium Vision. Have been here at Pixium since 2019. And at Pixium Vision, we are a publicly traded company based in Paris, and we are developing a bionic vision technology system called Prima, which is actually targeting vision restoration in patients who suffer from dry age-related macular degeneration. So at Pixium Vision, we are creating a world of bionic vision for those who've lost their sight. As I mentioned previously, we are a publicly traded company, so please be mindful of any forward-looking statements. A bit of an overview about Pixium Vision. The company actually was established in 2011. Our primary focus is neuromodulation in ophthalmology, and we have three core areas of competence based primarily in our offices in Paris. The first is we have an expertise in brain-machine technology development. Second, in proprietary algorithm development as well, with a specific specialization in creating computer algorithms for image simplification. And third is the use of artificial intelligence to improve the user experience and the visual experience for the patients who we've implanted. We are developing the Prima retinal implant system, which actually helps visually impaired patients regain sight through a process of neuromodulation, which I will explain a bit later in the presentation. It is today the only ophthalmology treatment modality with the potential to restore vision, actually rather than halt or manage visual decline. We are entering the final development stages for the company. So far, we've implanted 7 patients in 2 feasibility studies, actually 9 patients in total with the recent start of our final pivotal study here in Europe. In the phase 2 ongoing feasibility studies, we actually exceeded our primary endpoint, and we've demonstrated successful letter reading in the central retinal area. We have also validated the proof of concept in dry age-related macular degeneration, which today is a disease that has no current therapeutic solution. And we do believe that the Prima system can become the first therapeutic solution in dry AMD, a market which we initially estimate to be around $1.25 billion. And the next development steps for the company are to complete our Primavera pivotal study. We expect a readout of that study sometime in late 2022, perhaps into early 2023, and to actually continue our US phase 2 feasibility study with completion of enrollment of all patients by the end of this year. We have an experienced management team based in Paris and the US. Collectively, we have over 100 years of experience in medical device technology development and commercialization. We also work very closely with Lisa Olmos-Ducou, who's our chief medical advisor, and she is a retinal surgeon based at the University of Washington School of Medicine, Harborview in Seattle. As we are really leading the way in research in the treatment of dry age-related macular degeneration, we have surrounded ourselves with the top scientific advisors and thought leaders in the field. There are 2 most notable that I'd like to mention on this slide. First is the co-founder, Professor José Alincel, who is the founder of the Vision Institute here in Paris and is also the chief of ophthalmology at University of Pittsburgh Medical Center, as a world-renowned ophthalmologist with a specific interest in developing technologies to treat blindness. And also, we work in very close collaboration with Stanford University and Professor Daniel Palanker at the Hansen Physics Lab in the development of our implant technology, which I'll explain in a moment. A brief word about dry age-related macular degeneration. Actually, AMD is a very well-known retinal degenerative disease, and it's actually the most prevalent in the world. Today, there are 200 million patients that suffer for age-related macular degeneration, 80 to 90% of which have the dry form, and 20% of which have the wet form. The wet form actually today has a treatment. These are anti-VEGF injections, known as Lucentis Eylea. These 2 drugs for treating the wet form actually represent around $10 billion in sales annually. However, the larger form of the disease is the dry form, and today there is no approved treatment for dry AMD. What you see here in the center of the screen on the right is a typical image of a visual field that a patient with advanced dry AMD actually has. So you can see that they maintain some peripheral residual vision, but their central detailed vision is lost as it advances to the later stage of the disease. The onset occurs mostly around 60 years old, and we know that in advanced dry AMD, or otherwise known as geographic atrophy, when the patient is considered legally blind, this has a significant impact on quality of life. It also impedes their ability to read. They can't move about freely or take public transportation and have difficulty with other daily tasks. We believe that Pixium's Prima system can become the first approved dry AMD solution. Now I'd like to show a couple of slides concerning the Prima system itself. So the Prima system is actually a miniaturized photovoltaic wireless subretinal implant. You can see an image there on the penny. In the center of that penny, that is the actual implant itself. It's a 2 by 2 millimeter implant that's 30 microns thick, meaning it's thinner than a human hair. And if you were to put the implant under a microscope, you'd see 378 independent functioning electrodes. The implant itself is made out of what we call a photovoltaic material, so it converts light energy into an electrical signal. In the disease of dry AMD, the photoreceptor cells in the most inferior layer of the retina no longer function, and those cells are responsible for converting light into an electrical signal. So basically, our implant takes the place of the non-functioning photoreceptor cells. That is the implant that I mentioned that has been developed in collaboration with Stanford University, for which today the company has all rights for indications in all geographies worldwide. In addition, there are two external components that communicate with the implant. Those consist of a pair of glasses with a camera and digital projector, and also a pocket processor itself. The camera is actually responsible for capturing the images, and the pocket processor or pocket computer actually has two primary functions. First is to capture and process the signal and the images that the camera actually sends to it and simplifies those images. And the second action and responsibility of the computer processor is actually to create artificial light that is required to stimulate the implant. And on the next two slides, I'll explain the mechanism of action and then show a brief animated video demonstration. So the Prima system actually consists of a three-step visualization process based on the three communicating components I just mentioned on the previous slide. In step one, we generate a signal based on the surrounding environment. So after the patient undergoes surgery and the implant is actually placed in the subretinal space, 4 weeks later, when the retina heals, the patient comes back for implant activation. At that time, we put the glasses on the patient, we switch the system on, and the mini camera will capture images of the environment as a video stream and send those images to a pocket computer. The pocket computer then transforms those images into a stimulation signal using proprietary algorithms and sends the signal back to the glasses. In the second step, we transmit the signal to the subretinal implant, and that is done by the glasses projecting via laser a pattern at the back of the eye based on signal received from the image analysis system, and the laser then will stimulate specific cells of the subretinal implant. In the third step, the signal is then converted into retinal stimulation. And so what happens is the stimulated implant cells will use the photovoltaic properties of the implant to transform the energy received from the laser beam into an electrical current or stimulation. And then that electrical current will stimulate the retina, leading to optical nerve stimulation and a brain interpretation of the stimulus itself. On this next slide, I'd like to actually show you an animation of what I just described. So here you can see in the deepest layer of the retina, the photoreceptor cells, which actually have died. The surgeon will create a small incision. We inject the implant in the subretinal space. Silicone oil or gas is applied to reattach the retina. The patient comes back 4 weeks later for switch on. There you can see the glasses being placed, the image being captured, and then the laser energy being sent back through the pupil to stimulate the implant itself, where the rest of the visualization process occurs. Now, in the 9 patients that we've already implanted, the 7 in the 2 feasibility studies and 2 that have just undergone implantation in our final pivotal study, we've had excellent clinical results. On average, patients are actually able to improve their visual acuity on a letter reading chart by 5 lines. And just to put this in perspective, typically 2 lines of improvement on a letter reading chart are needed to demonstrate an improvement in visual acuity. So we've well surpassed that in our clinical studies. And we've actually also published this data in the Journal of Ophthalmology last year. So what I will show you now is actually an example of a patient 12 months after implantation undergoing a word reading test with our newest generation glasses. And basically, the patient will need to identify the letters on a page, read the letters, and then state the word in a predefined amount of time. If they have 100% accuracy, that's considered a successful letter recognition or word reading test. In addition, as a control, we then remove their glasses, we change the word, and then we ask them if they can read actually the new word on the page without using our system to see exactly how good their vision is without the aid of our implant. Here you can see now the patient scanning to find the first letter. On the left, you can see what the camera is actually receiving, and on the right is what the implant is capturing. So we can see that he can see the letters already. He identified the P and the O, the I. He identifies the 2 S's, the O, and the N. Poisson is fish in French, so he was actually able to identify that word. Now, as you can see, we actually have removed the glasses. We've put his regular reading glasses that he uses for his peripheral vision and changed the word to elephant. We've asked him now if he can identify any of the letters of the word, and as you can see, he said he couldn't see anything so far. And so you can see that he said he can see some scribbles, but is actually incapable of reading any letters or seeing the word. And this is typical of the improvement we see with our patients post-implantation. Thank you for your time and attention.